Section 3.6, the derivatives of log functions. And so kind of finishing up looking at the different types of functions that we work with on a regular basis. How do we differentiate log functions? So using kind of a similar little technique that I use with the inverse trig functions, but kind of explain why this is what it is or how this comes about. But ultimately, just like there, just as long as you know how to find the derivative, right? You don't need to know how to derive it or where it comes from, but I like to do that just to show you why these things are what they are. But ultimately, you just need to know how to find the derivative of a log function. So we're going to let y equal log base a of x. Now, if you remember when we did our little log review, remember you had a conversion that you could do between a log equation and an equivalent exponential equation. So to say that y equals log base a of x is equivalent to saying that that base a raised to the y power equals x. So those are equivalent equations. So to differentiate y equals log base a of x, I could equivalently differentiate a to the y equals x. So here's going to be that implicit differentiation again that we used, just like with our trig function, inverse trig functions. So we're going to differentiate with respect to x. I didn't write my little statement, but the usual. We're finding d dx of each side of our equation. And this is implicit differentiation. Differentiating with respect to x, we're looking for dy dx. So with respect to x, the derivative of a to the y, remember that's our exponential function base a. We said the derivative of a to the y is the function times the natural log of its base. And then the chain rule says for exponential functions, I also have to multiply by the derivative of the exponent, which in this case is y, so the derivative of y dy dx with respect to x. The right side is our derivative of x with respect to x, which is 1. So then as we typically do with implicit differentiation, we then solved it for dy dx. So I get dy dx equals 1 over a to the y times natural log of a. Then we can come back up here at the top and say, well, wait, I can replace y with log base a of x, because y is equal to log base a of x, so the y that I have here I can replace with log base a of x, since those are equivalent. So now I've got 1 over a raised to the ln of a, log base a, of x, times the natural log of a. Now a raised to the log base a of x, this is again a property of logs, exponential function base a, raised to the power of the log base a of x, will simplify to just x, because again the exponential and the log are inverse functions. They undo each other. So I end up with dy dx equal to 1 over x times the natural log of a, which a was the base of your exponential function. So ultimately, and like I said, this is what you need to remember, so this is why it is what it is. The derivative with respect to x of log base a of x is 1 over x times the natural log of a. Now we're going to get into the whole chain rule thing here in just a second as well. So what if the argument is not just x? What if it's something else or something more? Now, special case, we deal with our natural log function quite a bit, right? That log base e. Just like our exponential functions, we deal a lot with exponential function base e. Same thing is true for log functions. We deal, primarily with log functions base e. Remember, and I told you when we did the review that there are really just 2 bases that you see used on logs with any regularity. And that's log base 10, which is the log function, and then the log base e, which is the ln function, right? So log of x is base 10, ln of x is base e. And just like with exponentials, we deal extensively with the log base e function. So the derivative of ln of x, right, log base e, is just 1 over x. Because if you remember again, natural log of e, log base e of e, equals 1. So I mean, this property is still true regardless of the base of the log. But for base e, it's a simpler derivative because of the fact that natural log of e is 1. So just like with our exponential function base e, whose derivative is e to the x, the derivative of e to the x is e to the x, the derivative of ln of x is simply 1 over x. Now, don't forget, though, the more general case. Even though we do deal primarily with log base e, so in that case, it is still 1 over that argument. It's still 1 over x, but I also need to multiply that denominator times the derivative of the times the natural log of the base. And that gets forgotten because we just simply don't deal with other bases very often. All right, so I'll have an example for you to remind you. Now, the chain rule, and this should make perfect sense, and I think I gave you in the list of functions back when we started the chain rule. If I'm going to differentiate the natural log of x, or ln of x, it's 1 over x. But then our chain rule, if I have something more than just x there, if that argument is itself a function of x, then I would think I would need to multiply by the derivative of that argument. Right? That's our basic chain rule process. The outer function would be the log function, and the inner function is the argument. So for chain rule, let's say I'm looking at the derivative of natural log of u, where u is a function of x. So d dx of the natural log of u is still 1 over u, it's 1 over that argument, but then u being a function of x, I then multiply times the derivative of u with respect to x. Or if you prefer, and I think most people do, the function notation, the derivative with respect to x of the natural log of a function is 1 over the function, because that's the argument, 1 over the argument, times the derivative of that function, right, times the derivative of the argument, or simply, and this is the way I'll do it, I'll take the derivative of the argument divided by the argument. But now again, that is only for ln, that's only for natural log or log base e. If you have log base something else, then down here you would also tack on a natural log of whatever that base is. So if we had log base 3, then it would be the derivative of the argument divided by the argument times ln of 3. And again, I'll have an example for you. But like I said, most of what we see is ln, just because those are commonly occurring functions in the real world. So differentiating, for example, number 1, I've got f of x equals natural log of x squared plus 10. And again, whichever way you prefer to do this, here's taking it as directly from the definition, f prime of x would be 1 over the argument times the derivative of the argument, which would be 2x plus 0, right? Or just 2x. Or if you prefer, let's just go straight to this. And so this is what I'm going to tend to do, I think, with the bulk of my examples. I'll take the derivative of ln of an argument as the derivative of the argument divided by the argument. All right, and it just simplifies it, takes a step out of the way. But if you prefer to do it the other way, like this, that's fine. Whatever is easiest for you to follow. So a few different examples. Number 2, and I wrote them out over here in a little more detail. Number 2 is an example of one with a different base. So let's say y equals log base 5 of x e to the x. So again, my first recognition here is that my main function, I do have a composition here. My outer function is the log function whose argument is the inner function, and that's typical for any log function. Just like the trig functions and inverse trig functions, the arguments are the inner functions. So the log function is the outer function. What is the derivative of a log function? Well, we said it's the derivative of the argument. So here's my derivative of the argument, d dx of x e to the x, divided by the argument, which is x e to the x, but then since I have a base other than e, I also need ln of 5, ln of the base. So it's 1 over the argument times the natural log of the base times the derivative of the argument, or as written. Okay? But again, don't forget this. It's going to happen because we just don't simply work. We simply don't see that many logs of different bases. Most of what we see is log base e, ln. And so after you do a bunch of ln's, you tend to forget that if there is a different base, you also need this in your derivative. Okay, so be careful. Now we still have to deal with the actual derivative of the argument, right? So that takes care of the log function part. Now, just like with all of our other processes, I have that derivative that I have to find. Now that your derivative there is just done based upon the type of function that you have. You know, it's like we keep saying, once you say, okay, I need to differentiate this, I don't care about the rest of that function or that expression. I focus on the derivative. So there's a product. So I think we're going to have to use product rule there. So like I said, you have to recognize all these different processes in conjunction with or mixed in with everything else we keep talking about. So it's kind of a circular process. You know, you have different functions and processes all mixed together, and you just have to kind of recognize which one applies at a given time. So once I label that I'm going to find the derivative, my question is, how do I differentiate x e to the x? And that's a product, so I'm going to use product rule. So here's our derivative of x e to the x, which would be our first derivative of the second, which derivative of e to the x is e to the x, plus the second times the derivative of the first, the derivative of x is x. Now again, the denominator, I'm just carrying that along, right? There's no derivative down there. I'm done with that. And then the numerator, I can clean up a little bit, so I just rewrote that as x e to the x plus x, e to the x. And then the denominator I didn't have to mess with. But then you can also recognize with this one, there is some simplification as well. We're always looking to simplify. So I could then factor out an e to the x in that numerator times x plus 1 over that denominator, and I can divide out then that common factor of e to the x. And I'm left with x plus 1 over x times the natural log of 5 as your derivative y prime. Okay? So again, general process, it's chain rule. For a log function, the derivative of the argument divided by the argument, and in the case of a base other than e, I also need the natural log of the base. After that, it's differentiating the argument, whatever is necessary to do, and then we simplify from there. Number 3. And again, just kind of giving you some combinations of different functions, because I know visually sometimes I think the issue is we see it a certain way and maybe visually we're not clear on exactly what the makeup of that function is. So I'm looking at this function y equals x cubed times natural log of the sine of x. And again, I think a lot of this has to go back to your basic understanding of notation. That's x cubed times that natural log function whose argument happens to be the trig function sine of x. Right? So again, remember, this is not a product. This is not ln times sine, right? It's function notation. It's the natural log of the sine of x. Now, if I wanted to multiply a natural log function times a sine function, I'd have to write this. I would do ln of x times sine of x, right? So be clear. I mean, these are the kind of mistakes that I see made all the time with these functions, and it's just not clear, understanding the basic notation. I think it's the biggest issue. So that's why I keep harping on that. All right, so otherwise, I mean, I'm looking at y as a product of x cubed and that natural log function. So we're going to differentiate using product rule. All right, that's the outermost function that we're working with. So what does our product rule say? It says that y prime then is the first times the derivative of the second, which is that ln of sine of x, plus the second, which is the natural log sine of x, times the derivative of the first. So that's just product rule. That's all that is. Then we go in and we deal with each of the individual derivatives. All right, so here's our y prime, x cubed. It's fine, carry it down. I need to differentiate the natural log of the sine of x. Differentiating a natural log function, it's the derivative of the argument. Derivative of sine is cosine over the argument. All right, so the derivative of ln of sine of x is the derivative of sine, which is cosine, divided by the argument, which is sine. plus, I've got ln of sine of x. Again, I just carry that down, and I need to differentiate x cubed. The power function derivative of x cubed is 3x squared. I'm done with all the derivatives. Now I'm just going to rewrite a little bit. Now notice I've got a cosine over sine right there. I can rewrite that as cotangent. Right? Let's use some of our basic trig, to simplify or rewrite into a simpler form whenever possible. So I'm going to rewrite cosine over sine as cotangent. X cubed times cotangent of x. And in the back end of it, I just brought the 3x squared in front of the natural log just because it looks better. Right? Technically, nothing wrong with writing it that way, but that just looks a little nicer. So like we said, sometimes we rewrite just because it's visually more appealing. So I've got x cubed cotangent x plus 3x squared ln of sine of x, and that is y prime. That is our derivative. All right. So I mean, these are pretty straightforward. I mean, there's nothing tricky here once you come to grips with the fact of how do you actually differentiate a log function. And then again, we have to recognize all the other processes. Now, number 4, this one kind of leads us into a discussion that we're going to have later in this section. All right, now look at this function that we're working with. I've got g of x. This is a pretty ugly function. G of x equals the natural log of all of this stuff. Now, you could differentiate this as written as a log function, where the argument of this log is a fraction. I could apply the rule for differentiating log functions, which says take the derivative of the argument, which I would have to differentiate that using quotient rule, and then I divide that by the argument, which is that, and then I end up with a complex fraction. And I think just even thinking about it, you can see what kind of mess you would lead into. Now, it can be done, but it probably would get pretty ugly, and there's going to be a lot of simplification that you're going to have to do there. So this is going to be one of those cases where if you recognize that there's a way that you can put this function into a form that's easier to work with, then we're going to do that. And working with these log functions, remember we did a discussion on the properties of logs back in that first little review section that I did with you. And there were some basic properties of logs that said the log of a product can be written as the sum of logs. The log of a quotient, as what we have here, can be written as the difference of logs, log of the numerator minus log of the denominator. And there was also a power rule that allowed us to take the exponent out of the argument and place it in front of the log. So I want you to recognize properties of logs. If I have the log of a quotient in this case, there is that property of logs, so I'm just rewriting using properties of logs first. Now this is still just my function. I'm not differentiating here. I'm rewriting the function. So g of x equivalently can be written as the log of the numerator, 2x plus 5 cubed, minus the log of the denominator, x minus 1 to the 4th. And then the power rule for logs says that you can take this exponent in your argument and you can bring that to the front of your argument. So natural log of 2x plus 5 cubed can be written as 3 times the natural log of 2x plus 5. Now be careful here. I'm not differentiating. I am rewriting the function using a property of log. So this is not our power property, or differentiating a power function. Now I see that happen. It's like, but wait, I brought the exponent to the front. I have to reduce by 1 and not. No, but that you're not differentiating here. You're using a property of logs to rewrite the function. So that's 3 times ln of 2x plus 5. And equivalently minus, I could rewrite the back end as 4 times the natural log of x minus 1. Those are properties of logs. Now I'm going to differentiate. But you look at now what I'm differentiating compared to what we were originally differentiating. And I think I've made life a lot easier for myself by using the property of logs to write that original function g of x as this. So now I can differentiate 3 times the natural log of 2x plus 5. Well, that's a constant 3 times the derivative of that natural log, which is the derivative of the argument. Get this to cooperate. the derivative of the argument, so there's the 3. Come on. There's the 3. Times the derivative of the argument over the argument. And now again, that's g prime. I've started the differentiation process. And then the same thing with the second one. 4 times natural log of x minus 1, so it would be that constant 4. My program is hanging up here a little bit. So that constant 4 times the derivative of the log function, which is the derivative of the argument. Now the derivative of x is 1. Derivative of 1 is 0, so the derivative of x minus 1 is 1. I'll get it straight here in a second. Divided by the argument. All right. So again, each one of those work the same way. So it's a constant times the log function, so its derivative, y prime, would be the constant times the derivative of the log function, which is the derivative of the argument divided by the argument. And then the same thing with the second one. And that's it. I'm done with the differentiation. After that, it's just, cleaning it up. So I've got 3 times 2. I could write that as 6 over 2x plus 5 minus 4 over x minus 1. And that is our derivative g prime. Right. So what started out as a really ugly function, now without that natural log there, without this, you're stuck with quotient rule. Or you could rewrite it and use product rule like we talked about before, but that's a quotient rule problem. So keep that in mind as we get a little bit further along in this section. If I can express this as a log function, then I can use properties of logs to rewrite the function. Okay? Number 5, I've got f prime of x, or find f prime of x, if f of x equals natural log of the absolute value of x. Now this is something I want to look at actually for us to use later. All right, when we get to finding antiderivatives or integration, which is the process of essentially reversing everything we're doing now. All right, so if you have the derivative, what is the original function? So that's where this is going to come into play. So I want to look at this. Because we already know what the derivative of ln of x is. We showed that earlier. That's 1 over x, right? But what about the derivative of the natural log of the absolute value of x? So what I did was I broke this up as a piecewise function. We love our piecewise function. So here's our function ln of x, absolute value of x. Now, depending upon the value of x that you plug in, now normally, and maybe a reminder too, I don't think I've reminded you of this yet in this section. For log functions, remember that the domain of a log function whether it's ln of x or log base a of x, whatever the base happens to be, the domain of ln of x, your argument can only be positive. All right. Now, whatever the argument is, if it's x, then x has to be greater than 0. If the argument is x plus 2, then x plus 2 would have to be greater than 0, or x would be greater than negative 2. Because we always talk about different types of functions. How do you find those domains? So the domain of a log, your basic log function, the argument, maybe it's best to say it this way, the argument must be positive. Log functions are not defined for arguments that are negative or 0. So for log of x, natural log of x, the domain is 0 to infinity, but the natural log of absolute value of x, the domain would be all real numbers except 0. You still can't plug 0 in there because ln of 0 would still be undefined. But at least now I've expanded the domain of the function to include negatives as well. So I'm just going to make a note here for that as well. For ln, we'll go ahead and do it that way. Log base a, because that way it doesn't matter what the base is. the domain there would be all real numbers except 0. So I could take everything up to not including 0 and then everything on the positive side. Okay? Because of course there's a difference between those two functions. All right, so getting back to our function. So how do I differentiate this? So now that I can plug in negative numbers, well, we've talked about this before when we were dealing with some limits with absolute value. Some of us kind of understood a little bit of that. Some of us, it really, I don't think, made much sense. But think about this. If I plug a positive value into this, then the absolute value doesn't mean anything. In other words, if I plug 3 in place of x, the natural log of the absolute value of 3 is the same as the natural log of 3. So as long as x is positive, then the natural log of the absolute value of x is exactly the same as ln of x. The absolute value is not going to change that. But if I plug in a negative value for x, which I can here because of the absolute value, it makes it positive, right? But it's not the same as the ln of x, it's the ln of the opposite of x. So for example, if x is negative 3, and I plug negative 3 into that function, then its natural log of the absolute value of negative 3, which is not ln of negative 3 because that's not defined. The absolute value forces that to be ln of 3, which is the opposite of what you plugged in. That's the discussion we had back when we were dealing with the limits of, and we talked about one-sided limits and all that stuff. But regardless, and again, ultimately, I'm really just interested in you knowing the outcome of this, but I've explained why it is what it is. So regardless, I can, take the derivative then, but it depends on what value for x you plug in terms of how or what the function looks like. So in the case of ln of negative x, we'll just do that one first because it's on top. If you differentiate this function, right, it's a natural log function, so its derivative is the derivative of the argument, which would be negative 1, divided by the argument, right? So the derivative of the argument negative 1 divided by the argument, which is negative 1x, gives me negative 1 over negative 1x, which simplifies to 1 over x. Now, for ln of x, without the absolute value or the parentheses or anything else, nothing changed from before, right? I mean, the ln of x, the derivative is still 1 over x. It's like, okay, well, what's the big deal, right? I mean, we knew that already. The natural log of x, the derivative is 1 over x. But now, what I'm looking at, and like I said, and this is why I say save it for later. When we get to the reversing of this process, and I ask you, if this is my derivative, what is its antiderivative? What is the original function? The original function is not just ln of x, it could be ln of absolute value of x, which is a broader function. Okay, so yeah, tuck this away for now. It's not something that's going to be critically important at this point, but tuck it away, and we're going to come back. We'll mention it back again in chapter 4, into chapter 4, in chapter 5, when we start with integration and antiderivatives, and I'll remind you of this. Okay, so stick it in the pocket somewhere, and we'll come back to it. Logarithmic differentiation. Okay, now this is going to go back to, when we did this one, all right, and we talked about using those properties of logs to rewrite the function. And so this is going to lead us into what we're fixing to talk about, logarithmic differentiation. That if I have a function that's written in this form as the log of something, I can use the properties of logs to rewrite that function into a form that's easier to differentiate instead of having to differentiate that big quotient in that case. So what we do in this situation, and again, just like when I talked about implicit differentiation, remember I told you implicit differentiation doesn't just specifically apply to implicit equations. You could do it with explicit functions just as well. It works the same way. We just don't have to do it because we don't need to. Same thing is true with a process like logarithmic differentiation. Logarithmic differentiation can be used for any function that you want to differentiate, what I'm fixing to show you. The deal is, I don't always need to use it. With functions that are explicitly written as y as a function of x, I don't need typically to bother with this if I have a fairly simple function to differentiate. Now, the whole point here is going to be to rewrite the function into a form that's easier to differentiate. That's the whole point. You know, that continues to be a theme. Here's a function, find its derivative. If the function is ugly or if the derivative is going to be complicated or take some time to do it, maybe I can write it into a different form that's easier to differentiate. That's what we're targeting in this section, or in this part of it. So what we do for logarithmic differentiation is we use the log as an operator. Just like, you know, perform the same operation to both sides of an equation. I can take the log of both sides of an equation, or ln. We'll use ln because ln is the easier one to work with in terms of the derivative. So we use the natural log as an operator, and we perform or take the natural log of both sides of an equation. And then we use implicit differentiation from there to differentiate the equation. So in other words, look at example number 1. I just left it here. I've got this equation, y equals, right, 3x minus 4 to the 4th times x squared minus 2 to the 5th. Now we've dealt with equations like that before, where we said, okay, there's a product rule, right? I can use product rule to differentiate that function, and that may work perfectly fine, okay? And product rule is definitely applicable here with chain rule and so forth. The other option, we said, well, you could take it and multiply all that stuff out. Probably not a good choice, though, when you have larger exponents. I mean, it's doable, but it just takes time to do it. So, yeah, I agree. I could do this or find the derivative here using the product rule, and that's a perfectly viable option, okay? Let's look at doing it a different way. Let's take the log of both sides. Let's take the ln of both sides of this equation. So the left side, I have natural log of y, and the right side then is natural log of all of this stuff. And our reason for doing that, you know, is kind of, again, the ends justifies the means. I can now use the properties of logs, like we did with that previous example, to rewrite this right side of the equation into something that's a little bit easier to differentiate, using the rules for differentiation of log functions. So that's what I did in the next step. So I left the ln of y over here. Now again, notice I'm not doing the derivative yet. I am simply rewriting this equation. So I took the natural log of both sides. I then rewrite the right side using the properties of logs. So the property of logs here says that the log of a product is equal to the sum of the logs. So that would be the natural log of 3x minus 4 to the 4th plus natural log of x squared minus 3 to the 5th. And then I went ahead and used the power property, and I brought the exponent in front of the log. So I kind of combined those into one step. But the log of a product is equivalent to the sum of the logs, and then the power property, I pulled the exponent out in front of the log. And so now we're set up similar to the one that we just did. I can differentiate those functions, and the derivative of the log functions is pretty straightforward. So I've got the 4, the constant, and then the derivative of ln of 3x minus 4 is the derivative of the argument divided by the argument. There's the constant 5. The derivative of the natural log of x squared minus 3 is the derivative of the argument, which would be 2x, divided by the argument. And then I just cleaned it up after that. 4 times 3 is 12 over 3x minus 4. 5 times 2x is 10x over x squared minus 3. That's the right side. Now the left side, right? The left side was natural log of y. I want to differentiate ln of y. Now remember, we're differentiating with respect to x. So again, maybe I should write this. I am finding d dx of ln of y. All right, I'm finding d dx of this. That's our implicit differentiation. So the right side we took care of. Once we wrote that, just rewrote it using the properties of logs. We differentiated as a log function. The left side, I'm differentiating ln of y. Well, again, I'm differentiating a log function now. What's the derivative of the natural log function? Well, it's the derivative of the argument divided by the argument. What's the derivative of y with respect to x? Well, it's y prime, right? It's dy dx. That's our implicit differentiation. Divided by the argument, right? So y prime over y, or 1 over y times y prime. So that's our differentiation on the left side. Now, ultimately, we're trying to find dy dx, right? We started with y equals, we want y prime, so I solve it for y prime, which means I'll multiply by y, right, to get the y off of the left side over to the right. So multiplying by y, and I've now got this. And then I can take one more step here, because the original equation says that y is equal to all of that. Well, I can replace y right here with what it's equal to. And now I have everything in terms of x. So in addition to the part we already had. Now that may look really, really weird and look maybe difficult or confusing, but it's really not. If you break it down piece by piece, I'll show you another example, right, and what we're doing. But it relies upon two things. It relies upon, first, use of the properties of logs to rewrite the original equation. And then secondly, it relies upon use of implicit differentiation. Okay? Now, again, choosing to do that, it was an alternative. You know, like I said, that particular function could just as easily, I could differentiate that using product rule. Okay? So here's a case where, you know, using the logarithmic differentiation maybe was not the best choice. I could probably do it just as easily the other way. But again, it's an alternative. Okay? Now, in some cases, you don't have a choice. You know, it's just like implicit differentiation. I told you that always works regardless of the function. We just don't have to use it if we have an explicit function of x. Same thing is true with log functions. Even though I can use it for any function, it's typically not going to be a method of choice unless it just really makes my function easier to work with once I apply the properties of logs. Now, there are some functions that yet you do not have a choice. That logarithmic differentiation is the only option. If you look at number 2, y equals the sine of x raised to the x power. Now, you know, we talk about with derivatives, when we go to differentiate a function, the first question is, what type of function do I see? Yeah, there's a trig function there, sine of x, but that trig function is the base of that function, sine x raised to the x power. So my next question would be to you then, since I see an exponent there, is that function an exponential function, or is it a power function? Because remember, if it's a power function, I can maybe differentiate using the power rule. If it's an exponential function, I differentiate it as an exponential function. But I'm going to tell you now that that function is neither an exponential function nor is it a power function. What does it mean to be a power function? A power function has a base that has the variable. That's what we've got here. The variable is there. But the exponent has to be a constant. And it's not. So by definition, this is not a power function. All right, well, maybe it's an exponential function. What does it mean to be an exponential function? Well, for an exponential function, the variable is in the exponent, so we've got that. But the base, if you remember, has to be a positive constant. And that's not what I have here. My base here is the sine function, which could be positive or negative, depending on the value of x. So my base is not a constant. So it has to be a positive constant in the base with a variable exponent to make it an exponential function. So it's not exponential either. Okay? So here's a function that I cannot use power rule here. So I can't do something like x times the sine of x raised to the x minus 1 power and apply the power rule that way. No, that doesn't work because x is not a constant. I can't do this as an exponential function because the base is not a positive constant. I can't just say, well, it's the derivative of that would be the base times the derivative of the exponent, right? We're using chain rule and all of that. Okay, so it doesn't fit those two categories. So here's a case where I have no choice but to use logarithmic differentiation. So here's the process again. What do? I take the log of both sides, and I use natural log just because the derivative for the natural log is easier than the derivative for logs of other bases. I don't have to worry about the ln of the base part. So ln of both sides. Then I use the property of exponents to rewrite the right side, right? So that exponent x can be brought to the front of the log. Again, property of exponents. And now I've got this function, or this equation, I should say, ln of y equals x times the natural log of sine x. So the left side I'm going to differentiate as natural log function. The right side, notice, is now a product. It's the product of x times natural log of the sine of x. So I'm going to have to use product rule to differentiate the right side. So here's the left side. When we said natural log of y, I'm differentiating a natural log function, which is the derivative of the argument divided by the argument. That's y prime over y, or 1 over y times y prime, as I wrote it up there. Either way, some people prefer it one way, some prefer it the other. But for a natural log function, it's simply the derivative of the argument, which is y prime in this case, divided by the argument, because we are differentiating with respect to x. And again, I'm not writing it every time, and I'm going to ask that you do once you apply, or to show that you are using your implicit differentiation to get to that next step. So there's a derivative of ln of y. So it's the argument, derivative of the argument divided by the argument, so y prime over y. The right side, we're going to have to differentiate as a product. So it's x times the natural log of sine of x. So our first times the derivative of the second. Now we've seen this one before. The derivative of sine is cosine divided by the argument, right? The derivative of the argument divided by the argument, plus the second, which is ln of sine of x, times the derivative of the first, derivative of x, which is 1. I'm done with the derivative. Next step, I just cleaned it up, so the left side is still the same, y prime over y. I didn't mess with that yet. I'm just rewriting the right side. There's our cotan of x again, cosine over sine. And then I've just got ln of sine of x. I can drop the 1. Now, solving for y prime. So I've now got y prime equal to y times all that stuff we have on the right side. X cotan x plus ln sine of x. Now I need one more parentheses here. Make sure you're multiplying, right? Because it's the y times the entire side of the equation. Okay? And then lastly, don't forget this, because we can replace y with the original equation, because that's what y is. Y is equal to the sine of x to the x power. So I can replace y down here with sine of x to the x power times all this other stuff we already had. Okay? That's logarithmic differentiation. Now, come test time, what I will do, because I know it's not always easy, some of these, to recognize, when to use implicit differentiation necessarily, when to use logarithmic differentiation. I'll give you one specifically and say, here, use logarithmic differentiation. Now, that's not to say that you can't use it for some other function that you're differentiating. It's just typically not going to be necessary. So I'll give you one specifically and say, here, show me that process of logarithmic differentiation, so you know how to do it. But otherwise, it's not one that you're going to use on a regular basis. Same thing is true with implicit differentiation. I'll give you one and say, here, use implicit differentiation. Show me the process. Okay? But otherwise, you're free to use it anytime you want. It's just not going to be necessary. I've got these tacked on, and these I actually gave you early on. I think it must come up in the homework somewhere, and in one of your homework problems you may need to refer back to this. This is how we define the number e using limits early on. We said that e was equal to, the limit as x approaches 0 of that expression, 1 plus x raised to the 1 over x. It's also equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. And each of those would approach 2.72. As in the first case, x approaches 0, as in the second case, x approaches infinity. Right? So there may be some reference that you need for that in this section. So there you go. All right, that's it for this section.